Hi, my name is Monia Hossein, and this is my Lab 5 on Slinky Drop. Here is an overview of what I'm going to do: the introduction, Newton's second law and formulas, experimental setup, glow script, calculations, models, what-if questions. Introduction / purpose of the experiment. Purpose of this experiment is to analyze the motion of a falling Slinky and determine the impact of its surroundings on its fall. During this experiment, we will also see how the bottom of the Slinky stays in place when it is dropped. The system is the Slinky, surroundings is earth and air. Assumptions: no other forces are acting on the Slinky. The Slinky starts from rest. The fundamental principles we need to know for this experiment is Newton's second law. The net forces are equal to the change of momentum over the change in time. The net force is equal to F Slinky plus F grav plus F drag. The Slinky forces act as a tension force in the opposite direction as gravity. And we have our F drag formula. Experimental setup. I will use tracker to track the movement of the bottom of the spring in the video. I will record the data from the video from YouTube, starting from the bottom of the Slinky that started from rest and to the time it fell. We will then create a computational model of the spring movement using fundamental physics principles and the known times. Then we will compare the computational model with our tracker model. Then we will determine the reason for differences between the models. Here is my tracker video. I first screen recorded the given Slinky video, and then I set the calibration stick to the man's height, and for this lab we will assume it's 1.75 meters. I started plotting my points when it was dropped from rest, starting from the bottom of the Slinky. So this is my tracker analysis, and this is the initial mass, 0.25 kgs, the calibration stick, 1.75 meters, which is the assumption. This is my initial Y position, and it stays at this position from 0 seconds to 5.267 seconds. This is when it was not dropping. Well, it was dropping from his hand, but the bottom of the Slinky remained motionless or constant or unchanged. And then the bottom of the spring changes, so it begins to fall down at that time and the ending time of 8.167 seconds. And this is the tracker final position. So here's my glow script code. Here are the initial conditions: mass, position, and velocity is 0 because we started from rest. Here is gravity, and I guess and check the drag force constant. Here is the ending time of the Slinky not falling down yet towards the ground. Here we have the drag force and F-net formulas and the momentum principle for both sections, the velocity update and position update formulas. The only change is the time where the Slinky began to fall and ended. Here is my model. As you can see, they have different slopes, but they have a similar beginning. Possible errors must be the drag force constant because I guessed and checked, or my tracker data is off, possibly due to when the Slinky was falling. I had probably messed up my points. Also, not all forces were included, and we assumed the person's height, so calibration could be off. So here is where it stayed constant or relatively the same for both the experimental and computational model. But here I'm guessing it has to do with my tracker plots because I was kind of unsure about the calibration stick. Also, I don't know if this is like the right position. It's maybe the right alignment didn't occur. So let's answer the what if questions. Does the bottom of your model Slinky stay stationary just like in the video? I would say yes. If you see the chart over here, the model position being red, it stays constant or unchanged in the beginning. So that means that it does remain stationary until it is done being extended. It's now just the Slinky, not extended. So it began to fall. And so let's think, why does the Slinky temporarily remain stationary? At the bottom of the Slinky, the forces in the Y direction, gravity and the Slinky force, completely cancel out. The magnitude of the tension force pulling the Slinky up and the magnitude of the force of gravity are equal in opposite direction. That's the end of the video. Thanks for watching.